Hello, I'm Arya,
And I'm Alan.
and we're presenting on our work this year using reinforcement learning to make drones fly in swarms. So first off, why would this be necessary? Well, if you look at lots of disaster relief situations, for example, rescuers have to search through hundreds or thousands of these demolished buildings in short periods of time, looking for human survivors. And it's often very hard for rescuers to get to places like the second floor over here, because it's relatively inaccessible. But this is a far easier task for a drone to get through because it's nimbler and it can move freely in all three dimensions. However, the problem with using a drone is that, as Matt said, they often have short battery lives, but also they're expensive, and the ones that can do this sort of search are usually pretty large and unwieldy. So there's a lot of room for improvement. And one of the areas of exploration is using a swarm of drones at once, because manufacturing individual drones is a lot cheaper, they're a lot nimbler, and they're more economical in general.
So our proposal is to use reinforcement learning, or RL, to train virtual drones that can swarm in an environment with imperfect information. So it's important that we have imperfect information because when we want to deploy drones into an environment, they don't know what they're going into. And if debris falls or if situations change, we want them to be able to adapt on the fly. Most of the current drone stuff has been done with perfect information, such as Intel's drone show at the 2018 Winter Olympics. They scouted the environment months in advance and mapped it out to create their drone and light show. But we want to do this with imperfect information. That's why our project is different.
So more formally, imperfect information would just be the information that the drone can see right around it, not the entire environment as far ahead as it wants.
So, what is reinforcement learning? So, reinforcement learning is a type of artificial intelligence, and as with all artificial intelligence, its purpose is to find a solution to the problem that we don't know the answer to. And nothing embodies this more perfectly than reinforcement learning. What we do in reinforcement learning is we throw an agent into an environment knowing absolutely nothing except the actions that it can do, and it knows the rewards that in its current position. So say that we throw a reinforcement learning agent into Mario Brothers. So all it knows is the block positions, so where every one of the blocks is and where Mario is. Its current actions, so it has 4 different actions, so left, right, up, down, also like throw a fireball. And it knows how far it's progressed in the level. So
that would be its reward.
That would be its reward. So based on whatever random actions it takes, it'll be given a certain reward. In the beginning, it'll know basically nothing, and it will make random moves, and it will be very, very bad. But over time, as you keep training it and running it over and over again, it'll learn what certain actions yield greater rewards, and it'll be able to get to the end of the level.
So we have the problem modeled out now, but then we're looking for a solution, the algorithm that can actually solve our problems. And then in 2017, OpenAI released an algorithm called Proximal Policy Optimizations that does a very good job of solving this class of problems. Alan's going to try and explain it to you.
So proximal policy optimization is a reinforcement learning algorithm developed by OpenAI, and it was just released 2 years ago in 2017. I could explain it to you, but there's a lot of math behind it that I don't really understand. So we're going to show you an example. So this is Hopper, which is a gym environment, a virtual gym environment that gives you a leg, and you want to make it be able to hop a certain distance. And so if we put this into a reinforcement learning problem, the state or the current observation would be the leg pose. So where are the current joints? What angle are they at as the robot falling down? The reward would be the distance traveled, because that's what we want to maximize and be able to get the hopper to do. And then we pass this into our reinforcement learning model, or PPO, and then it spits out actions. This is not Hopper, this is Walker. Yep.
Yes. Now, PPO is great for these simplistic problems, but it really shines when you give it a much more challenging problem. So for example, in this case, there's a humanoid robot that's trying to run around and get to the red circles, and it's constantly being pelted with these little blocks. And this is obviously a very challenging problem to model, especially when the only reward given is just how far you progressed. It learned how to walk all on its own, And it's a little dirty, but it gets the job done. And I should point out that it seems like flying a drone isn't that challenging of a task, but actually, flying drones is really hard. And the reason it's hard is because when a drone receives an input, all it receives is the speeds at which the four motors move. And that's not necessarily intuitive. So there's a lot of work that goes behind even using the joystick controls that we're comfortable with for flying drones. So for example, when the drone expects motor velocities, and the human would want to output roll, pitch, or yaw thrust controls, there's a controller that has to sit in between and somehow convert between the two mediums. And there's a lot that goes behind that controller. So what the common industry control is using a PID controller, which stands for Proportional Integral Derivative Controller. And a lot of words, basically what it means is, it takes in the difference between the current roll and the roll it wants, and the current pitch and the pitch it wants, and it would do the same for yaw and thrust separately. And then what it does is it takes the derivative, so how fast things are changing, it takes the value, and it takes the integral, meaning the sum of all of it over time, and then it adds constants before them, and essentially uses all of that to model an action that the drone should take.
So for our project, we wanted to do two parts. We wanted to do a virtual simulation so we could train our drones because breaking drones would be very costly. So we wanted to find a physics engine to do our simulations in. So first we looked at Gazebo, which is very high fidelity and CUDA compliant, which means we can GPU accelerate its training. However, Gazebo proved to be very, very slow in training. So even after hours of training, these were our best results.
At this point, what the drone is trying to do is get up to a height of 1 meter and just stay there. It's not working. And the reason it didn't work is because we realized that Gazebo was just too slow.
Yeah, and also we were controlling the rotor speeds, and to get it to be able to hover at a certain height, it has to be very, very precise, and there was just too much noise in Gazebo to handle it.
So what we moved to is we made a couple of observations. We noticed that the Crazy Fly drones, or CF for short, were already doing these position calculations on board their firmware, and that there were existing tools that could convert that firmware from C to Python, which is what we were using for the rest of our project. So we realized that if we just use the firmware and we tell the firmware where the drone is and the actions we're taking, it can tell us where it expects the drone to be in a future point in time. And we can couple that with a little bit of noise just to make it not completely reliable, like real life, and throw in a visualizer so that we can see what it's doing. And we end up with a much more stable simulator. So we built CF Firm, which is based off the Crazy Fly firmware, and it was able to successfully train for several different tasks. The biggest improvement was to the speed, because by removing individually modeling each rotor and modeling each component of the drone in the realistic physics engine with all the airflow, the firmware was able to take a bunch of shortcuts because it was optimized specifically for this drone. And what that meant is that while Gazebo ran at about half of real time, the firmware ran at almost 2,000 times real time. And what that meant is that when we then wanted to train a simple task like hover, it successfully did it in just about 7 minutes.
So hover, this is, we took about 2 months trying to do this. It was kind of hard. But, so if we put this into a reinforcement learning problem, we have to first define a reward function very, very well. And these are the constraints that we put on the drone. So we have a direction reward, so we want it to be able to hover at a certain height, and the direction, which is just the difference between the drone's current position and the drone's final position. The distance reward, which is the distance between where it is and where it wants to be, and then the movement cost, which we added because initially when we trained it, it would get to the final point and then it would like wiggle back and forth and spaz out a lot. So the movement cost is
It's
to
a
make it
penalty for moving around.
So hover. So this current state in the reinforcement learning problem is the current and desired positions. So that's 6 inputs. The reward is the function that we just showed you. And then we pass that into our model and it spits out the actions, the desired velocity vectors.
At this point, it was about December, and we realized we really needed to get to some more complicated tasks if we ever wanted to get to swarming. So we rapidly tried a different thing. So the next thing we tried was getting the drone to move from any point A to any point B. So point A is in blue, point B is in red, and you can see that the drone is able to stably get there and sit there. So again, we used what we learned with the movement costs and the directions, and it worked almost right out of the box, which is really nice. From there, we wanted to model obstacles. And we all wish that if we wanted to model obstacles, we tell the drone this, and it just works. But it never works like that. So don't ended up being a whole other problem, because the biggest issue with these reinforcement learning algorithms is they expect a fixed number of inputs. And in the real world, there might be one person, there might be 3 people. So how do we model all of the numbers of people using the same amount of space every time? And what we ended up with is we ended up using a potential field control. What this essentially means is it treats each obstacle as a positively charged field. So say, for example, a magnet. And then you treat the drone as a magnet as well. And then you simply pass it what direction the magnets are pushing it away. And that way it has a sense of where the obstacles are and how far away they are.
And then so our inputs for the drone can just be the gradient of where we want the drone to go along these fields instead of inputting every single obstacle. So this obstacle end, it's kind of slow, but it gets the jump.
Yeah, so what we ended up doing is we modeled a bunch of obstacles. We stuck with just cuboids because we figured that a lot of objects could be modeled by just putting bounding boxes around them. But the beauty of the potential field controller is that you can model any shape obstacle you want. So in this task, the goal is still to get from point A to point B, but this time there are random moving obstacles in the way.
And it looks like the drone's going through the obstacles, but it's just the angle of the shot because we kind of move the camera around while we recorded this.
Then we move on to swarming. The first task we did was we started all the drones in random positions and told them to try and get to the center without crashing into each other. And this we ended up taking a lot of what we learned from the obstacle ends, because at the end, all of the other drones are obstacles. So we tried to be super conservative to make sure that they really wouldn't crash, so we penalized them really heavily if they did crash. And sometimes that ended up with them drifting a little, which we argued was a reasonable compromise between drones crashing and not getting super close. The other reason they can't get super close to each other is because when you have a physical drone, like this one, it spins all its propellers, which means there's a lot of turbulent air right underneath the drone, which means you can't fly other drones directly underneath. They'll just get messed up because the air is not consistent.
And then, so we got to our final goal, which is swarm swap. So we just took what we learned from the static swarm end, and we applied it to this thing. So we initialized a bunch of drones at 2 random points, and we wanted the swarms just to swap positions without crashing into each other, and while avoiding obstacles at the same time. And so this was our final product. And you can see that they count each other as, you can see like the fields because they're like going around each other and not crashing.
Okay, at this point, we realized we had reached the conclusion of the simulation portion of our project. And what we ended up with is that the swarming problem can be solved with reinforcement learning. And more particularly, it works well extending existing controllers. So plenty of controllers exist that simply use potential fields and model the obstacles and try and get around them. But they don't necessarily take the best paths, and they don't necessarily account for a lot of different factors like short battery lives or the amount of time taken.
And stable results require varied training. So we have to train our drones in a lot of different varied environments to be able to get them to be able to do an environment they haven't seen before.
So because a reward function is simply just a sum of smaller rewards, so as you saw with hover, we were doing, for example, penalizing it for movement, rewarding it for pointing in the right direction, rewarding it for getting closer. If you want to reward it for other things, it's very easy to do. You just add to the end of the reward function and say, get there with as high of a battery life as possible, and the drone finds the most economical route.
Okay, so super glue is not super. So on each of our drones, if you look at them, we put tiny little markers so that they can be tracked within the black box by these Vicon cameras. And we initially attached them with super glue, but every time they landed, all of them would fall off. So every time. So we ended up switching to 2-part epoxy, which is very much stronger.
You use it to bind metal to metal each year.
Yeah.
So it's pretty intense.
Cool. So next part. So great. So where is the thing that you all came to see? The demo? Yes, the demo.
We will get there, but before we do, we just want to explain one last thing. Okay, we want to explain the physical setup. So if you look around you, if you see all of these cameras in the ceiling with the red circles, these are all part of a Vicon motion capture system. Now Vicon generously agreed to loan us the entire system for the year, which is excellent because it would have been hard to get it otherwise. Each of these red circles are strobe lights that flash in the IR spectrum, so outside of the visible range, and then the cameras are looking to see the reflections back. And what that means is, it can look at all of these reflective dots, like you see on this, it's called a wand, I don't know why it's called a wand. So all these reflective dots, if multiple cameras can see where they are in 3D space, then they can use the relative positions to figure out where it is very accurately. And it's extremely accurate. It's about 0.5 millimeter of like inaccuracies at 500 times a second. So we then connect this motion capture system to two PCs. If you turn around back there, you should see those two like antennas poking out at the top next to that monitor. That's what controls the Crazy Flies. That's this little radio, and it's sitting on top of the two PCs that we use. We need two because one runs Windows and one runs Ubuntu. Vicon software only runs on a Windows PC, so all the wires run around the back down there, and then they plug into our code, which runs on Ubuntu.
Yeah, so it passes in the current drone positions in the space into our scripts, which spit out certain actions that the drone should take, and then we send that to the Crazy Flies through the Crazy Video.
Now I'll answer the question you had right there. What do you do in the real world where you don't have a beautiful motion capture system and you don't get 0.5 millimeters of accuracy? The limitations of robotics is that there's essentially two problems that you're always trying to solve. One is how do I get it to move? And then two is a little less intuitive, is how do I know where I am? Because if you're a drone flying in the air, it's really hard to tell whether you're here or here. And the only way to really do that is to use a bunch of different mechanisms. One of which, for example, is SLAM. So you put a LiDAR piece on top of your robot, and it tries to simultaneously map out the spaces around it and localize itself within them. So simultaneous localization and mapping. These are developing fields, and there's something that we can't do. These are things that grad students work on for 7 years at UC Berkeley. So we simply don't have the time to do it. And so motion capture is the most commonly used shortcut within a lab space if you're trying to just deal with one half of the project. So this cuts out the whole localization aspect by just giving it to us, and then we can focus on the movement control. Okay, so at this point, we'll move to our demo. We'll need a bit of a rearrangement because we need a little more space here. I will say that we have about a 70% success rate with the swarm. I was here till like 9 p.m. yesterday with Alan trying to get this to work. So we need you to remove the front 2 rows of chairs. Anyone who's uncomfortable with the possibility of the drone being flying,